You keep the lights on or turn them on? What would you prefer?
On top of
You think I'm on? Alrighty. Share screen. Get rid of this. Whatever. All right, yeah. Thank you guys all for coming today. And then today you got something exciting planned because we're gonna run Grover's algorithm on an actual quantum computer today. But before we do it, I figured I might as well briefly go over just how to actually make an oracle in practice for Grover's algorithm. I have like a small example laid out for you on 3 qubits, but the overall procedure, like it really extends well to like, any number of qubits. Usually you need something called like a general multi-control gates, right? So you can, similar to how you get a control bit on C naught, you can get like multiple control bits for a single operation. It is implemented on Qiskit, like the IBM's quantum computing, like, stuff that they have, but a lot of quantum hardwares don't necessarily actually have that gate. Like they might have it, they might not, but yeah. So briefly, let's go over what a reflection over an axis is generally. Here's an example of like a reflection over the x-axis, right? Like you have this general vector here, you reflect over the x-axis, boom. You have, and here's a general reflection over the y-axis. You have the vector here, reflect over y-axis, boom. In general, reflecting over some axis means holding the components that lie on the axis constant and multiplying the components that lie on the other axes by -1, right? Reflection over the y-axis, you hold the y-axis components constant and you multiply -1 over the x components, right? And then likewise for x, that actually is, it's consistent with over higher dimensions or any other context as well. So recall in Gover's algorithm that after performing a uniform superposition of all possible states, we perform Grover iterations to slowly shift the state vector from lying on the superposition axis um, to, we shift it over to lying almost entirely on the mark state or key direction, right? This axis of all that's the axis that is an equal superposition of all the states that actually return 1 when you plug it into the oracle. So yeah, Grover rotation is, if you recall, is composed of 2 steps: a reflection over the unmarked state axis, right? And a reflection over the uniform superposition axis, right? And doing those in sequence essentially rotates the original state vector by some certain angle. So a reflection over the unmarked state axis is where essentially you leave all the components of the state vector that lie on the unmarked state axis, right? All the states that don't return 1 when you plug it into Oracle. Uh, and you multiply by all the components that lie in the orthogonal direction, right? So all the states that um do lie that are marked states by -1, right? So I think I summarized right here. Just multiply all the, what this effect turns out to be is just multiplying all the marked states by -1, but all the other states unchanged. And then reflection over the superposition axis, right? A lot of textbooks, if you ever get into this, they call it an inversion about the mean, right? Inversion is just like a reflection, right? And then mean is like, what they mean by mean is like the superposition axis, essentially just like the average of all possible states, right?
yeah.
So yeah, we what this looks like is that we leave all the components that lie on the uniform superposition axis the same, and then multiply all the components that lie in the orthogonal direction to that, or perpendicular direction by -1. No, it might be kind of hard to try and visualize what states are orthogonal to the uniform superposition direction, right? But it turns out you don't really actually have to think about that. However, if you do want like a more concrete idea of what that looks like, I can walk through it after this lecture. But yeah, in general, it just does this. All right, so how do we actually implement these reflections in practice? So as I mentioned earlier, we make use of multi-control gates, right? The general form of the CC knot or Toffoli gate in higher dimensions. And we will go over implementing these 2 reflections the reflection over the superposition axis and the reflection over the what do I call it? Unmarked state asset axis. Right, in the three qubit case, so we can use the Toffoli gate or the CCX, but I do think it serves as a nice example because it generalizes really well for how you actually implement these in higher dimensions. So the first thing I want to talk about is the CCZ gate, right? And it's selective applying -1 phase to states, right? Before we delve into like the meat and potatoes of actually how to implement these, I want to talk about the CCZ gate, right? Which is like multi-control two control qubits, and the third target qubit is applies a Z gate on the third target qubit if it two controls are on, and how it is used to selectively apply -1 phase to the states. First off, let's discuss what the CCZ gate. Oh yeah, I just talked about it. Uh, Yeah, and the Z gate, since it only applies -1 phase, if the qubit it is acting on is in the one state, it turns out the CCZ only applies -1 phase to the state if it is exactly the state 111. And leaves all the other states unchanged because the Z gate does nothing, right? Remember? Yeah. So here's like a brief truth table, like, over all the 8 possible states when you have 3 qubits and like what they do on the states, right? Like, leaves everything unchanged except for the 111 state, which applies a -1 sign. So it turns out this result is actually huge. If we have a way to selectively apply -1 phase to the state vector, if and only if the state is 111, this means that we can easily create a way to selectively apply a -1 phase for any state, i.e. only apply -1 for, like, for example, like -1 to the 010 phase, or only apply for the 110 state, right, etc. All you have to do is strategically apply X gates in the circuit before you apply the CCZ gate, so that whatever state you want to mark turns into the 111 state right before the CCZ gate. Does this make sense? Not, it's fine. I'll go through a brief example. Yeah. After you apply the CCZ gate, the state vector will gain a -1 phase since it was in the 111 state right before the CCZ gate was applied. And it is simple enough to turn it back into the marked state, whatever it was, right? Now with a -1 phase. The cool thing about this is that you never have to worry about accidentally applying -1 phase when the state vector is not in the marked state. Remember, you're applying X gates in such a way that the state only turns into the 111 state when it is the marked state. That means unless your state is the marked state, the state vector will never gain a -1 phase because it will never turn into the 111 state when the CCZ gate is applied. Well, at the time when the CCZ gate is applied. Thus, since it won't be in the 111 state and the CCZ gate only applies -1 to the 111 state and does nothing for all other states, you never have to worry about incorrectly applying the -1 phase. So here's a brief example I mentioned, and hopefully it'll make everything clicked. So let's say we want to only apply the -1 phase to the 100 state, particularly, right? This is what the circuit would look like, right? This is, these are the input qubit registers, right? And then we only apply X gates right in front of the second qubit and the third qubit, right? So think about what happens. If whatever input we have, right? Unless they're exactly the 100 gate. Oh, shoot.
We'll just
Damn, okay. They locked it.
Normally it is 15 minutes past is when it happens.
Okay, I'll pause the recording for a sec.
I think you probably just bring him up.
Wait, Loki, since you're the only person here, just want to come up here and just like look at my screen while I explain. I'm only in front of you because like. Okay. Yeah, so let's say this is exactly the 100 state. Once we apply the two X gates on the second and third qubit, it'll turn to the 111 state,
Yeah.
right? You apply this is CZ, so again, -1 phase, and then you convert it back into the 100 state, and then you measure, right?
Yeah.
Think about if it happens for any other state though, like the 000 state, when you do these gates, it will never turn into the 111 state, which means that the CCZ gate does nothing.
Yeah.
Right?
Yeah.
It's pretty clever, right?
Yeah.
And that applies for all the other states, that you can think of, the eight possible states for 3 qubits, right? It'll never gain a phase of -1, and this sequence of gates will never do anything to it unless it's exactly the 100 gate. And then I think I walked through it a bit more explicitly here. 100, 100, 1, 2, -1, which is the same thing as -1 phase over the 1, state. Apply X gate again, so -1 times 100, and this is your final result. All right, so how do we actually do a reflection over the unmarked state axis, as we mentioned earlier? So let's say, for example, that our marked state is the 101 state, right? It'll return 1 if the circuit is in the 101 state, and it'll do nothing for all if it's any other state, right?
Yeah.
Then a reflection over the unmarked state axis, right? And equal position over superposition over, all the other states that return 0 means that we only apply a -1 phase to the state vector if and only if the state is in the 101 state, right? Because if we're reflecting over this axis, then we just apply -1 phase to the axis that is orthogonal, which would be this, and leave this unchanged. So this is exactly what we're doing. If it is any other state, given what we know about the CCZ gate and how to use it, this becomes really trivial. Reflecting over the unmarked state axis is exactly the same as selectively applying -1 phase to the 101, right?
Yeah.
So this is the sequence of qubits that you're going to use, right? Just apply an X gate in the middle, CCZ, X gate measure, right? And then we'll walk it through again for the 101 state exactly. 101, 101, apply X, turns 1, 1, 1, CCZ, so applies a -1 state. It'll apply nothing for any other state. -1, and the selected turn it back, so it gets to -1, 101 state with a -1 phase.
Yeah.
And just for completeness, here's a truth table for the circuit again.
Yeah, only 101.
Yep. And apply CCZ gate, it turns into this, and this is the only state that gets a -1 phase applied. And then, apply the X gate again in the middle, then bam, that's the final result. Pretty clever, right?
Yeah.
All right, so here's something a bit more tricky. How do we actually do a reflection of the uniform superposition axis, the other part of the Grover iteration? While it initially seems challenging to figure out how to reflect over the uniform superposition axis, once you realize it is just reflecting over the 0, state in the Hadamard basis, aka if we apply Hadamard on all the qubits before and after this sequence of gates, right? This becomes really straightforward. So this is the circuit of selected applying the -1 phase to the 0, state, right? I'm sure you're pretty familiar with this. Makes perfect sense. And then we just apply a Hadamard on all the qubits before and after, since reflecting over the 0, state in the Hadamard basis is exactly the same as reflecting over the uniform superposition state in the standard basis. Here's a full circuit. It's so easy. You just apply Hadamard at the beginning, Hadamard at the end. To cancel out. Hadamard is actually the inverse of Hadamard, so you just cancel those out afterwards, right? Because we only want to do this operation in the Hadamard basis and nothing else.
Yeah.
And then, I was thinking about putting the truth table, but it's like a pain in the ass. So I just, intuitively, I'm pretty sure this makes sense as well, right?
Yeah.
So something I just remembered. The CCZ gate isn't explicitly initiated for a lot of quantum computers, right? They may have it, they may not have it, but usually CC not or CCX usually is because it's a lot more important. It's like not important, but like more like elementary gate. A lot of people see it. So if you don't see an explicit CCZ gate in the architecture or like the gate sets that you can use, then you can just divine yourself by applying Hadamard before and after the X gate in the CC naught, right? Because Z is exactly the same as Hadamard, X Hadamard. Yeah, that's it. And then the rest of the lecture, I'll just walk you through an example of actually of running this Grover circuit, the 101 Oracle, on a actual quantum computer. So I know said you had to leave. Do you feel like you can stay for this or no?
Yeah, I can stay for now. For like the mark states, is it like arbitrary or is it like do you know which one you want to mark before you like approach Grover's algorithm?
So, okay, let's say you're doing Grover's algorithm, you're just doing Oracle. Obviously, we won't know, but because we're making it ourselves to run the circuit, like we do know. So we have to decide on a mark state before, create an Oracle for that. right? And then we run Grover's algorithm. But if you're given the Grover problem, then you would be given the circuit that works on a quantum computer without knowing what the Mark's data is. So you just have to run this sequence.
Mm.
Does that make sense at all? Or
So then how would it apply in like real world applications if like the Oracle, does it just exist that like it'll know which one's the mark state? Or is it like
yeah, so the oracle in premise is a black box, right?
yeah.
You don't know exactly how the function works, but you can work with it.
But does the
So
black box exist in the real world? Or is it
right now, I mean,
like a
I,
theoretical?
it's more of a theoretical thing.
Uh,
I guess like if there was a way to like perfectly converts like a classical oracle, right?
yeah.
And then turn it into a quantum oracle, without actually knowing the gate. Sure, it's
Yeah.
possible, but like, I do agree. It does seem kind of useless unless because we have to convert into a quantum oracle.
Yeah.
For many of the hard problems, they're just hard to find a solution. They're pretty easy to verify.
Uh,
Yeah. The classical circuit to verify it is pretty easy. And you just curve that up quantum of the quantum oracle. You don't need to know what it is.
um,
It's not actually a lot.
yeah.
So I guess like to paraphrase what this whole discussion was, in practice, yes, we will know what state we are using because we're coding it ourselves. But
Yeah.
in theory, for the problem, when you're doing the Grover's problem, you shouldn't know what it is.
Mm,
All right. I'll just give you some credit so you can run it yourself as well.
yeah.
Let's see. Wallet. I think it's no billing. Okay.
So right now this will be like a 3 qubit.
Yeah, yeah, yeah. 3 qubit billing. There we go. All right. What's your username or like favorite at all? You can pull it up your qubit as well. For everyone else that wants to like get some get some credits and run this themselves on their real quantum computer, just like feel free to shoot a message to us over Discord.
This is a new user interface.
Yeah, yeah. They upgraded from Qubit 1 to Qubit 2, and took me a minute to figure out where everything was, but
Superconducting underscore FKLVK.
FKLVK?
Or yeah.
All right, so I wish they'd implement like a search feature and make this so much easier. Bro, okay. FKL.
LVK.
You're in organizations, right?
Am I not?
Oh, you're not in the organization. Um,
Yeah, I was only part of the ACM like the tutorial.
gotcha. What's your email?
It's Michael YHXC.
What?
Sales.
Can you just type it? Bro, what? Maybe. Blah, blah, blah. Could you try again? Maybe it's because I didn't have the message. Oh, it says you're already a member of the organization.
Oh,
Uh, what's
oh,
your?
it's maybe G.ECLA. Is there a difference?
It does say you're part of it. So FKL.
LVK. I think would the G.ECLA make a difference for the unit?
Bro, okay, bro. I think if you go to invitations, it'll show. Refresh the page, maybe. Like refresh the page itself. We click on that. Oh, so sorry, back. This. Bro, what the? Could you go to your Gmail, maybe? Sorry. Yeah, yeah.
Mm. No, I don't think it's showing up. Maybe just take a moment.
Maybe.
Or maybe try logging into whichever one was in.
It's too much of a hassle. I can just like walk through this and just so we can get sorted out after
Yeah,
as
I think
well.
you can just walk through this on your computer first.
Gotcha, gotcha. All right. Hopefully, I might have to load more credits into this, but that's what it is. All right. Okay. So what you're gonna do is you're gonna open up a lab instance in Cubase Lab once you log in,
Mm.
and then you actually want to download a new environment. Go to environments is over here, right?
Mm.
And then click add. And then what you want to do is you're going to want to click the QBraid one, right? QBraid SDK and make sure it's version 0.110. It's
Yeah.
the newest one, it's the only one that actually works. Download it, and then, you know, it'll send it like install over here and then add. And then once you click more, you can look at the actual package that are downloaded in. You may want to update some of these, remove some of these if you want or not. But yeah, that's pretty much it. Go to the top, this line of code, right? Actually import the Kubernetes provider. This will be like a wrapper through Kubernetes where you can actually access client devices and schedule jobs.
Mm.
And then get devices, it'll give you a warning. You can ignore that. And then you can check out all the devices that are available right now, right?
These are the real
These are the real
world
quantum
hardware.
computers. Yeah. Some of them are like really, really good simulators as well, I think.
Mm.
But you can check in the devices panel, and then the red means it's offline. This is unavailable. And then the green ones are all I can access, like Anka. These are actual supercomputing CPU. And then this is like a simulator by AWS.
Mm.
But yeah, these are really, really good. And they're a lot cleaner than real on the devices. But yeah, this is just some lines for Qiskit that'll make stuff easier for me because I like to find my quantum circuits in Qiskit. I think there's other softwares you can use like Amazon's Braket and shit like that.
Mm.
But yeah, here's like a simple bell state, right? Draw it out. And then here's some shots running on the sample backend. Then this is actually how you access the real quantum device. You do the provider and then you get device using the ID, which is up here.
Mm.
and then this will just print it out. Metadata just to see like sort of what like how it works, the pricing, and then mm, stuff like that. I think
What is
you
this?
this is IQM's Garnet. It's like a quantum computer. And
Mm.
it's just a metadata for the device itself. I think you can look it up online, like what gate sets they have as well.
So are you choosing which computer to use
Yep,
or
right here. Provide the get device, and you just put in
um
the ID that you want from over here.
mm,
And then, I'm just gonna do 50 shots, right? And then just define a job where you actually use IKM Garant device dot run, and then this is a circuit you're gonna put in. You can do any like quantum circuit, like I use Qiskit because that's what I'm used to, but you can do like Broadcat, or you can load up an actual CASM file if you want. I
mm,
think it doesn't matter because they convert it all to CASM like in this wrapper, and then they put it into whatever circuit form that needs to be available for the device that they're running. Like for instance, like I made my circuit in Qiskit. I think this wrapper turns it into CASM and then converts that CASM into like Broadcat so it can run on Garnet,
mm.
right? And then you can use dot status just to see if it's like running or not, I don't want to burn through credit, so I won't like use it here because
Yeah.
it's just a bell state. It's not nothing very interesting. But yeah, you can keep clicking status to see if it's like loaded up yet, or like if it ran successfully, or like, and then once you do, you can just define you just get the results of the job because it'll return once it finishes running the QPU. And then this is just some like nice code to make it very easy to visualize. And as you can see, it is very easy. Sorry, that's just some deprecated code that I put it. And then here's where we actually define the reverse code for the 101 state. Like we talked about earlier.
Mm.
Sorry, I removed all the comments because I thought maybe it wasn't working very smoothly earlier. Like it wouldn't let me run the job. So I just cleaned the code a bit. I made it as simple as possible because maybe I thought that was the issue.
Yeah.
So it looks like this, but it's like I feel like it's pretty intuitive. Oh yeah, one thing to notice. The qubit wrapper, as of this moment, when I tested it earlier, has an issue with the CCX gate. Like Qiskit defines the CCX gate, the top of the gate, as CCX, right?
Mm.
But I think in the qubit wrapper, when it puts it into the like this line over here, once you like create a job and it converts into
Mm.
CASM, I think it puts into like it just has trouble with the CCX gates because
Mm.
I think Brocket uses CC not like they define it as CC NOT, and
Yeah.
then while Qiskit just finds a CCX, I think there's maybe some mix up over there, so it doesn't work as well. I got around it by just like transpiling the Toffoli gate into just like a bunch of CX gates and T gates, right? Which is an equal this is a value decomposition. This is exactly the Toffoli gate.
So you're manually making the
Yeah.
CCX. Mm.
Yeah. In the future, hopefully they'll get it fixed and so we don't have to do this. And that's like this is a code assuming like it does get fixed. But like, I figured, I want this to actually run today so you guys can run an actual quantum
Yeah.
computer. So I just did it like this. Exactly the same code, and it's pretty, even if that comes, it's pretty intuitive what I'm doing over here. This is the initial uniform superposition, and this is the first Grover iteration, right? Of the reflection of the on-mark axis, right?
Mm.
Because put an X over the middle qubit, and then this is the CZ gate, right?
Mm.
CCX with H on the X in front of the target qubit, right? And then this is your reflection of the uniform superposition axis, right? And then I think the number of times you want to run it for 3 qubits is like 2 times. So I just did this Grover iteration twice, and then measure all qubits. This is really ugly without the barriers that I usually use because I removed them. But yeah, that's what it looks like. And then I'll run this actually just so you can see the. Oh, sorry, just change it to. Oh yeah, make sure you change the qubit kernel.
Mm.
All right. Actually, measure that. Skip that because I don't want to do bell states. The cell. Okay, that's I want to skip. Then this is I'm just simulator. It's
Mm.
so much nicer. Right? Almost all in the 101 state, which is exactly what I want because
Yeah.
that's the um state for the Oracle. And then here's me queuing up the actual job here. Uh Pricing, I think it's like 30 per task and then like 0.145 per shot.
Mm.
So I think a nice even number would be 39, but I think that's more than the number of credits we have. So I'll just do 50.
Mm.
All right, let's run it. Christ, get this out of the way, please. Okay, is it not online?
Which one did you use?
Garnet. No! Oh my God, it's unavailable. What? That's so unlucky. It's just unavailable. Okay. It doesn't, I don't think it's elaborating. It just says unavailable. Okay, but it does take a credit, so it will return, run the job and give us the results back.
Mm.
I did run this earlier though, so like eventually it does return and there's you can use status to check if it. I'll run right now actually.
It says next available in 37 minutes, right? Just someone using it.
Oh, okay. Yeah, job is cute, so it did work, but I ran this earlier and these are the results. Very noisy measurements, but it does run Govers.
So if you scroll up,
Yeah, what's up?
what's this then?
Oh,
What's this compared to the, or is this just using the actual
oh,
hardware?
this is the actual hardware. This is a simulator that I used.
Oh,
Air backend is like a simulator by IBM, and then I just did it just to like give you an example to compare off of.
so for this they send it to the actual.
Yeah, I sent it to the actual quantum computer. I
Mm.
made the job over here, and they sent it to the quantum computer, right? And then
Mm.
this is just, once I check its status, it is queued right now.
Mm.
And then once it's, finished on the job and everything, it'll return the results, and then we can check it. And then I just plot in a histogram for easy visualization.
All right, yeah.
I'm so sorry. I guess you can't run it at least for another 37 minutes, but
Yeah. I think I got I logged into the one where I'm in the QCSA.
word. Okay, okay. I'll send you. Let me know the name, and then for everyone else as well, just like shoot me a message over Discord, and I'll give you credits so you can run quantum computers.
It's photonic.
Me go to
Oh, it says one
billing.
here.
It's like pending
Oh,
though. It's for this one.
yeah, yeah.
Very lucky. I think 150 is a good number.
How do these like credit system works? Like,
We buy credits with money, and then uh, you know, certain quantum jobs will require a certain amount of credits for them to run. Like
mm,
the pricing I mentioned earlier for Garnet is 30 per task. So like every time you do schedule up a task, it's a mandatory 30 credit fee. And then for number of shots is like 0.145 credit per shot.
mm.
I don't know why they made it 0.145 though. It's a really awkward number. I think it's like 200 shots is like nine credits exactly, which is like really annoying.
Yeah.
All right, yeah, transfer 150. All right, should have credits now. And then if you want, I can just like send you this Jupyter notebook with all of this and so you can like run it yourself.
Yeah, can you?
Yeah, for sure. Sorry, it is like if you want me to, I can like, go through it over again, put in like comments and everything and make it look nicer, but I
I
can
think
send you
it's
the raw
fine.
code right
I can
now.
just look at it for.
Gotcha. Yeah, remember, this is the algorithm defined exactly for the 101 state, assuming that is the only mark state. You can,
Change
toggle
it
it as
to,
well, yeah,
yeah.
to whatever state you want. All right, I think that's it for today.